Hi, I'm Ross Cutler, and I'll talk about the INTERSPEECH 2021 Acoustic Echo Cancellation Challenge. We'll first talk about the motivation and the goals of the challenge. Then we'll talk about the timeline and participation, the datasets and test framework developed, the base model, our results, and the learnings. As a background for why echo cancellation is needed, when a far-end person speaks, their voice is played on a local speaker, which is picked up by a local microphone, along with reflections of the signal and near-end noise. An echo canceller removes the far-end signal so they don't hear themselves speak. Acoustic echo is a top issue users complain about in Microsoft Teams and Skype. We wanted to stimulate research in acoustic echo cancellation by creating a challenge. To enable this, we provide a comprehensive dataset, a realistic test set, and an accurate and reproducible test framework. We released the datasets in January 8th. The blind test set was released to participants on March 3rd. The deadline for participants to submit their results was March 15th, and a week later we notified the participants about their results. 28 teams registered for the challenge and 14 teams submitted results. 6 papers were accepted from the challenge, including this one. This is our second AAC challenge. The main changes are as follows. First, we doubled the dataset size. We significantly improved the test set. The test framework accuracy was improved. We added a non-real-time track. We provided an extra month to complete the challenge, and we provided a new Azure service-based objective metric that is highly correlated to our subjective test framework. Our goal for the dataset was to capture 6 scenarios from 5,000 users, devices, and rooms. This dataset should be sufficient for AAC development. It includes far-in and near-in data for training data synthesis and can be used for learning room responses and distortions for training data synthesis. The 6 scenarios we captured include near-in single talk, far-in single talk with echo path change, double talk with echo path change, and a sweep signal for room response estimation. To capture this data, we utilized Amazon Mechanical Turk. We created a custom application that guided the user through device selection, setup, and the 6 scenarios we wanted to capture. For far-in data, we used 1,000 gender-balanced clips from the Edinburgh speech dataset for clean speech. For noisy speech, we used 2,000 gender-balanced clips from the Mechanical Turk single talk recordings. For near-in data, we had crowd workers read timid sentences. The final dataset was 30,000 recordings, which included 5,000 fully complete scenarios. Some challenges from the data include devices that have unknown cascaded processing, devices with different clocks from the microphone and speaker, the huge variation in device audio quality, and a huge variation in room responses. These are all challenges a real echo canceller also encounters. The provided training dataset is synthetic and is constructed as shown in this figure. For example, for near-end speaker, we sample a speaker from the crowdsourced dataset, sample 3 to 5 seconds of audio, and pad it to 10 seconds. For echo data, we sample a response function, convolute the far end with the response function, and then apply additional distortions such as clipping or a sigmoidal function. We provided a training dataset from real recordings, a synthetic training dataset, and 2 test sets. The blind test set is what was used in the challenge for evaluation. It includes 800 clips, 30 to 45 seconds in length, and includes these scenarios: long and varying delays, speaker and microphone distortions, stationary and non-stationary near-end noise, device DSP processing such as built-in AECs, audio glitches, and gain variations. Given the importance of echo cancellation in communication systems, there is no shortage of standards used to measure them. For subjective tests, there is P.831 that measures the subjective performance of network echo cancellers and P.832 for the subjective performance of speakerphones. For objective tests, P.168 defines ERLE among other metrics. P.862 defines the widely used PESC metric. IEEE 1329 defines terminal coupling losses, among other metrics. TIA 920 provides coupling loss criteria for speakerphones. G.122 defines AAC stability metrics. G.131 gives some useful relationships between acceptable talker echo loudness rating versus one-way delay time. And finally, G.168 provides a set of AAC metrics and criteria, but it isn't clear how to combine these dozens of metrics into a single metric or how well these correlate to subjective quality. The closest standard for our needs is P.831. We adapted the third-party listening test from this specification and combined the crowdsourcing approach used in P.808. For far-end single talk, we measured the quality of echo impairment rating from very annoying to imperceptible. For double talk, we measured both the echo annoyance and the degradation of the near-end signal. For near-end single talk, we measured the quality of the near-end signal using P.808. The solution was implemented as an extension to our P.808 toolkit and includes trapping questions, gold questions, rater qualifications, and analysis tools. For the far-end single talk case, we added the output of the AAC to the original loopback signal, delayed by 600 milliseconds. For double talk, we used the original loopback on the left side of a stereo playback and the output of the AAC on the right channel. For near-end single talk, we rate the output of the model directly. To compare the tool with objective metrics, we used 400 far-end single talk clips from the top 16 AAC models in the ICASP AAC challenge. We computed the Pearson correlation and Spearman's rank correlation coefficient between ERLE, PESC, and DMOS. This table shows these correlations are far too weak to stack rank AAC models with any accuracy. To measure the accuracy of the tool, we had 5 experts rate the quality of the far-end single talk scenario from the AAC challenge. We compared a single question survey, which asked only echo quality, with a 2-question survey, which asked both echo quality and other degradations. The 2-question survey significantly helped separate the echo and other degradations, as shown in the increased correlation with experts. This extension of P.831 shows very good correlation to expert raters. To measure the reproducibility of the tool, we ran a test with 3 AAC models plus unprocessed AAC 5 times on 5 different days with unique raters each day. The results shown here show excellent reproducibility. Our baseline model didn't change from the first AAC challenge. It is based on the NSNet model we have published previously in ICASP 2020. The microphone and far-end signals are first converted into frequency space using an STFT and concatenated as shown. These features are fed into 2 GRU layers followed by a fully connected layer to create an output mask. The mask is applied and an inverse STFT is used to get the results back into time domain. This model has a frame size of 20 milliseconds, a hop size of 10 milliseconds, and 1.2 million parameters. New to this challenge is an objective function that is highly correlated to the subjective results just described. Similar to what we've done with DNS-MOS for noise suppression, we trained a deep model on dozens of models passed through our test set. The correlation with human subjective opinion is shown in this table, which is excellent and superior to PESC and STOI. AAC-MOS is freely available via an Azure service. We will give more details on AAC-MOS in a future publication. Let's do a brief review of the challenge rules. For the real-time track, the method must take less time than the stride time to process a frame. In addition, the total algorithmic latency must be no more than 40 milliseconds. For the non-real-time track, there are no constraints on the computation time, but the model must look at most 40 milliseconds of future frames. The submitted papers must go through the normal review process and must be accepted to be eligible for the challenge. Finally, we use the previously described subjective evaluations to determine the winner. The 14 entries were evaluated with our subjective test framework. The first thing to note is that even though this test set is significantly harder than the first AAC challenge, the top performer exceeded the baseline by 0.13 MOS more than the winner of the first challenge. Therefore, the models are getting much better. Also note that the top 4 performers are all statistically identical. The submissions that had papers accepted are shown with stars. Note the correlation to acceptance and performance is relatively low. Finally, there is still about 0.6 MOS of improvement to be made. Using the submitted abstracts and published papers, we can do a high-level analysis of the submissions as a function of AEC performance. First is the model type, whether it used a hybrid approach with a linear AEC plus deep suppressor or a full deep model. We see that the hybrid approach is more common and most of the top performers are hybrid, but a fully deep approach can also achieve top performance. Some models include noise suppression, but we also see that is not needed to achieve top performance. In the real-time track, the first place winner is from the Chinese Academy of Sciences. Second place is from the Northwest Polytechnic University. Third place is from the company Evolve. Congratulations to all three teams, which significantly beat the baseline model. In the non-real-time track, there were no papers accepted and therefore no winners. In summary, the second AEC challenge was harder than the first, but the top performers did much better. In addition, there is still a lot of room for improvement for even better echo cancellation. Finally, for future challenges, we can add a stereo AEC track, mobile phone scenarios, and improve the aggregation of the overall result metric and make the test sets even more challenging. Thank you very much.
Great. So we now have time for some questions about the challenge. And I think the way to do it, either if there's people in the audience, they can ask questions first. And if there's the people online, you can ask questions just by typing it into the chat window. Any questions online?
Seems that Renhua has a question. You can just ask it as well.
I couldn't quite understand that. Could you, Ando?
As I understand, Renhua wants to type the question.
Okay.
Okay, so the question is why the top 4 teams have no paper accepted. Ross, do you have an answer for that? I don't.
It is statistically possible for that to happen. This hasn't happened. It wasn't just the top 4. I think the top 5 teams. This hasn't happened in our previous other challenges. So we've had 3 deep noise suppression challenges, 1 echo cancellation challenge, and in those challenges, at least 2 or 3 of the top 5 papers were accepted. We're not involved in the paper acceptance process. So there's always some randomness in the paper acceptance, and also, I guess, performance. Good performance doesn't necessarily mean, I guess, a paper that meets all the requirements for publication. That's and since I wasn't able to read the papers, I can't really speculate any more on that. I was able to read the abstracts. The abstracts seemed quite interesting. It's a shame that there weren't more of the top performing papers accepted. Okay, there's I guess a question that we mentioned the paper that an AGC and noise suppressor was used for the tests. Could you provide further details? Ando, do you want to answer that?
Sorry, where do you see the question? I don't seem to have it.
If you click on the question, it's a question mark.
All right. Yeah, it's not in the chat. So yeah, the data set was passed through the internal DSP-based AGC and the simple noise suppressor. This is basically to kind of even the playing field. So for example, we know that MOS scores are somewhat correlated with gain, and so if someone kind of amplifies the output, then that they would have an unfair edge. So that's why, for example, we passed it through the AGC, and then also similarly for things like small static noise, etc. So we wanted the echo cancelers who only like did the echo cancellation part and not noise suppression to kind of have a better chance to compete, because otherwise yeah, the raters will kind of be a little bit biased due to, for example, the Gaussian noise in the files.
Yeah, so this is shown, I guess, in figure 4 in the paper. We use, I guess, an internal AGC and noise suppressor, one that I guess is used currently in Skype. Well, unfortunately, we haven't made that open source. Maybe in the future we can use an alternative one that is open source, if that helps. If it would help, you know, just please add it in the chat.
Mm-hmm. But I can also add that like this was sort of a kind of precautionary measure, but I don't think that it really had a large impact. But listening through the files in general, I would say it had a negligible impact probably. So.
Yeah. Okay. Any other questions, either online or in person?
If not, I guess we can go to the next talk.
Yeah, I guess. Okay. There was just a comment from Christian about making it open.
Yep.
Yeah. So we do plan on having additional challenges, so we can work on that. That was, I guess, one of our original goals is to make all the tools used in the evaluation open source. This is, I guess, one of the exceptions. Okay. Please continue, Ando.
So yeah, let's get on with the talks.